Thank you. We're going to be talking about how to take a Pluto or phaser board and turn it into an easy to use real time radar system. My name is John Kraft. I'm an applications engineer for analog devices. I'm just going to do the first couple slides, just going over the hardware, and then I'm going to turn it over to Shane from University of Oklahoma. But we also want to thank Peter and Dr. Metcalf for their work on this project and their help. So real quickly, we'll just talk about the hardware, and then I'm going to turn it over to Shane for an overview of his GR Plasma auditory module, and then the changes that he made to GR Phaser to get the phaser implemented, as well as the Pluto implemented into his radar software, and then we'll show you some examples of that. So I think everyone's familiar with Pluto. I hope you are now. And actually, right after this talk here, I'm going to do another talk updating you on some of the new features of Pluto and where we're at with that. So I'll save that for later. But not everyone might be familiar with our phaser. It's our X-band phased array exploration platform. It's specifically intended for educational and some prototyping uses in the field of phased array radar and comm systems. This is a full 10 gigahertz system that has 8 channels of receive where you can adjust the gain and the phase of each of those 8 channels across the array. It has 2 transmit ports. They're switch transmit, so you could be one transmit or the other. And it uses a stretch LO system on the mixers, LO, to implement very wideband chirps, up to 500 megahertz FMCW chirps. So you get great resolution out of it. So this system has been released now for about a year and a half. It's available on our website, analog.com. We have oftentimes been out of stock on this system, but we just got in a big stock now. So it is actually, I'm happy to say it is in stock now. We have drivers and examples on how to use this system in Python or MATLAB, but what we were really missing and what we really wanted was an example or a system to use this with GNU Radio, to take advantage of all the features of GNU Radio and its processing power to use this in a true radar system. And so with that, I'm going to turn it over to Shane to talk about his work. Thank you.
So, hey everybody, I'm Shane. I'm a PhD candidate at the University of Oklahoma. I'm going to start off this talk talking a little bit about GR Plasma. For people who aren't familiar, this is an out-of-tree module that we developed at the University of Oklahoma a couple years back. And the main utility of it is doing real-time radar processing at really high sample rates. So we've tested this on GPU-accelerated processing specifically. So we've tested this on just a pretty standard desktop GPU, a 4080, and we're able to get several hundreds of mega samples per second real-time throughput just doing your range Doppler processing for your pulsed radar. So one of the big kind of architectural choices we made for this repository was to implement everything using the message passing interface. So each block is going to take as input a PDU, which is just a metadata dictionary and the IQ data that you actually want to process. And it's going to spit out another PDU that's done the operation you want to do. Another thing that we wanted with this repo is we wanted it to be as hardware agnostic as possible. So we have support for CPU backends, CUDA backends, OpenCL backends, and you can specify in each of the blocks, there's a little drop-down menu for which backend you actually want to use. And in the past, we pretty much only supported the UHD radios. So at the bottom here, I've shown just a couple of the blocks that we've implemented so far. So on the left, you have like just doing a monostatic radar with a USRP. So take an input, transmit waveform, output what you receive. We also have things like pulse Doppler processing, like I was talking about before, a match filter and a Doppler FFT. And we also have several waveform generators in there. So your linear FMs, polyphase coded waveforms, and various phase codes. So we wanted to take Pluto and phaser and port it so that we could use it with Plasma. Take the processing backend that we already had and add new hardware. So to do that, we've introduced 2 new blocks. They're both shown on the right. One of them, the one on the bottom, is the Pluto radar, and that just takes the Pluto standalone. And the top one is the phaser radar, which has a Pluto plus your phaser phased array board. And for the phaser radar, there are 2 operating modes. First, you have your pulsed mode, which is you send an arbitrary digital waveform through that input port. And the limitation of this is that you have to actually sample that waveform, right? So you're limited to the sample rate of your Pluto. And this is the only mode that's supported in the Pluto radar at the bottom. But if you have a phaser, it has hardware on board for doing FMCW waveforms. So you can, in hardware, generate high bandwidth chirps. And before you actually have to digitize it, you can do stretch processing, which I'll talk a little bit about next, to reduce the amount of data that you actually have to sample. And another cool thing about doing things in the message domain is that it makes control super easy. So one thing that we've added in this block is if you want to steer that phased array, you can just pass in a control message to change the angle, making it super simple. But you can also do things like real-time waveform adaptation or other parameter changes that I'm not going to talk about here. Right, so I'm going to just give a brief overview of the phaser radar block. The Pluto block is pretty much the same, just with fewer options because you're not controlling a phased array. I don't know how well that shows up there. But for the most part, the parameters are what you would have seen for any other radar or radio block that you've already used. You know, you've got your sample rates, your gains, that type of thing, which channels you want to use. But we've also added a few other useful options into this block. So for example, if you're processing pulses, it's a lot of data if you're trying to process an entire PRI of data, right? You might only care about a specific range swath. So we've added several options in there to where you can actually dice up your pulses to process only the data that you care about. And then on the right there, I have just various examples of, with the phaser block, you can specify your array weights, your gains, like if you want to apply a taper, and so on. And then on top of that, it has a bunch of radar options. So there's a little drop-down menu where you can specify if you want to operate in FMCW or in pulsed mode. And from there, you can tell it how many pulses do I want, how often do I want to send out pulses, what is my pulse repetition interval. For FMCW, I can specify how wideband I want that chirp to be, how long I want it to be in time, and so on. So yeah, just giving a very brief example of how you would apply this in FMCW mode, I have a flow graph shown here, which is a video. And like I said before, the phaser generates these in hardware. It has an oscillator on the board. And before you actually get the data on your SDR, it's going to apply stretch processing, which is just a simple multiplication on the board. And if you take your high bandwidth waveform, you can apply stretch processing and get back a beat frequency, which is proportional to how far away the object is. And this beat frequency is going to be a sinusoid that is a relatively low frequency and easy to sample. So hopefully it shows up well. Yeah. So as a simple example, going back a little bit. One thing I want to point out before I actually play this video is that I don't actually have anything connected to the input port for FMCW mode, right? It's just generating it itself. So when I start the flow graph, I can have my FMCW parameters on here. Again, I'm not sure how well it shows up. It is a 500 megahertz chirp over 100 microseconds, sending out 5 chirps. So I run this flow graph. Right now I have an antenna pointed away from the radar, a pretty directive horn antenna. I pull up the time domain after I sum the beams together on the phaser. And when I start pointing the antenna towards the phaser, I get these nice beat frequencies, which is just a sinusoid, plus a little bit of junk at the end because of some hardware like overshoot when you're actually generating the chirps. But I can move the antenna around and I can see a little bit of phase shift as I do that, and slight changes to the waveform. But overall, this just verifies that, yeah, with the radar block, I can get nice update rates on however many pulses or chirps I want. So a similar thing I'm going to show in pulse mode. And the only real difference here is now I actually have 2 sides of my flow graph, right? On the left side of that phaser radar block at the bottom, I have the waveform I want to transmit, which is its own block. In this case, it's just a chirp that's transmitting over 20 megahertz, within the Pluto sampling range. And on the right side, I'm only going to show the plot from the bottom. But what I'm doing is I'm taking the beams from the phaser, summing them together, and doing a similar time domain plot as I did before. So a similar example, again, just showing off pulsed mode. I'm sending out 5 pulses at a PRF of 10 kilohertz. So I start up the flow graph again, give it a second to boot up. and I get similar plots. You see, I'm sending for a small amount of time, getting the waveform I want. When I point it towards the antenna, I can see those chirps nice and clearly, right? And the way that I'm actually getting this nice, precise timing with the phaser is something called the TDD engine, which is pretty new and something that John will talk about soon. But yeah, as I move the antenna around, you can see that I'm getting shifts in this waveform, and again, a nice update rate for real-time processing. So after I'd verified that I'm getting good data off of this, I wanted to go out and actually test it. So I set up an over-the-air live demo with the phaser. So I have my little test bed that I put together in the bottom left. All it is a laptop connected via Ethernet to the phaser. I have that horn antenna I was using earlier, which is about 18 dBi of gain. And what I did was I set up the cart along this road, and I had one of my friends drive their truck all the way down the road. And the goal was really to see how high quality we could get the data and how far away we could get without any kind of external amplification, right? So we're just using the amplifiers on the phaser and on the Pluto. And the main data product that I wanted to get out of this is what's called a range Doppler map. And if you're not familiar, a range Doppler map is just an image where on the y-axis I have the range, which is how far away you are from the radar. And on the x-axis I have the velocity, which is just how fast it's going towards or away from the radar. So as the truck drives away, I would expect a dot that goes further away in range and increases in velocity, stops, and then turns around and comes back close to zero range where the radar is. So I recorded the data on a flow graph. I did all of the processing in GNU Radio and saved it to a file so I can make a pretty plot. And here's what that range Doppler map looks like. So when I first start off, this is, I think, the first processing interval of the radar. But when I first start off, you see that bright dot close to zero range. So when I start it, he starts driving. You can see that we maintain that dot all the way up until about 150 meters when he turns around and comes back towards the radar. Don't do that conversion from meters per second to miles per hour. I promise he was going under the speed limit. Yeah, so you could see a very clear dot, a very clear image of where that truck was throughout its course. So this says that, hey, we can get good range Doppler data up to about 150 meters with no external amplifiers, which is pretty good. So yeah, that is the main thing. All the processing, like I said, was done in GR Plasma. If you only care about getting a radar, you just want to see pulses and you want to do something with them, you don't actually need GR Plasma. All you would need there is what I'm calling GR Phaser, which has both the Pluto and the phaser radar. But really the idea with this was just make it as easy as possible to, if you have a Pluto or a phaser, just download this and instantly have a radar. Yeah, and if you would like to see more, like see the processing in action, just see us, how fast it updates. Analog Devices has a demo at the expo hall, and I can walk people through that if they would like me to go through it. But that's all I got, and I'm happy to take any questions.
So are there any questions? I will ask some if you don't, so you better ask. See, that works.
Just great talk. I just wanted to ask if in the interface for, I guess it was, I might get which one mixed up. I guess it was GR Plasma. If the independent receive channels are exposed when you're using the phaser board.
If the what?
The separate receive channels from the array. They said at the beginning of the talk that I think there were 8 receive channels. Yeah. Are the separate receive channels exposed, or is that all handled inside the block?
So what happens is the phaser actually beamforms those down to 2, and the block outputs, when it outputs its IQ data, it outputs those interleaved, so it'll have beam 1, beam 2 stacked on top of each other. And if I go back a little bit, I was only showing, let's see if I can get a better picture. You see that at the output, I'm actually summing the beam before I do anything. So yeah, if you want to do something with multiple beams, you can just not sum them and do whatever you want.
I don't see any other questions, so please give another round of applause for Shane. So
Okay, thanks. I want to thank Shane and Dr. Metcalf again. That was just, it's really impressive work. And if, for those of you working in the radar field, you know how intensive that signal processing is, and to be able to do it real time is very impressive. So yeah, thank you to you guys again. So again, my name is John Kraft, applications engineer for analog devices. I want to give you some updates on our Pluto software-defined radio, kind of some new things, a correction on something, to look for and possibly fix on your Pluto radio, and we'll go over that. I also want to thank Mark Thorin. Did his name get cut off? Sorry, Mark. That should say John Kraft and Mark Thorin. I want to thank Mark Thorin. He contributed to these slides, and he's always great to work with. That's always the one I don't pick up. All right. Okay, so just a couple things that I want to talk to you or go over today with this Pluto. First, what is Pluto? And specifically, I think everyone's aware of now, there's a Rev C that's been available for a year or two that exposes the second transmit and the second receive channel. So I'll just give you a quick look at that. And then I want to talk about how to incorporate Pi 80 IIO into GNU Radio. So this is our Python interface that you use in Python, but it actually works really well as if you incorporate it in a block in GNU Radio, and I'll tell you why you might want to do that or why that would be interesting. And then the TDD engine. So Shane talked about this cool TDD engine that's going to synchronize the transmit and receive buffers. This has been a long asked for feature of Pluto, and so we finally got it working really well. And it's what makes these kinds of radar things possible, where we can synchronize the transmit and the receive waveforms. And then I'm going to talk about a little issue with some Pluto ESD diodes, how to test for that, and then how to fix it on your Pluto if it is a problem. And then finally, a very cool context port forwarding. So if you have a bunch of Plutos or really a bunch of any IIO devices, how you can group those all together and transmit them all over one Ethernet, so you can control and stream data back and forth over one Ethernet cable. So Pluto, I think everyone is aware of Pluto. It's our little software-defined radio using the 809363 transceiver chipset. Natively, it's one channel transmit, one channel receive. There's a frequency expansion hack that you can do to increase its frequency range from 70 meg to 6 gigahertz, as well as instantaneous bandwidth up to 56 megahertz. It all communicates over USB 2.0, so it's a little bit slower for streaming data, but it does have quite a bit of memory on it for storing data, and then you can download that to your computer. With Rev C of Pluto, we expose the second receive and transmit channel, as well as the oscillator input and oscillator output. There's some videos on YouTube on how to access those channels and how to modify the programming, including the Python programming, to take advantage of those channels. I'll say though, when you do expose the second channels, the output data rate drops in half because we're using a slower data interface on the Pluto to the FPGA. So the output data rate gets halved when you do this channel expansion. But we're still using the 809363 transceiver, so none of the hardware has changed at all. It's still using this 809363 transceiver, but we're just exposing the additional channels that it has. Okay, so what are some ways that we can control Pluto in GNU Radio Companion? The classic ways, and ways maybe you've done, maybe you've seen before, is to use the Pluto source and sync block. These are very easy to use. They're very robust. They're installed by default when you install GNU Radio 3.10, and they're very easy to use. Another way to interact with Pluto or any IIO-based device is you can use the IIO attributes to assign attributes and then to stream data or to send data back and forth to any IIO device. The flow graph starts to get a little unwieldy because you have to set up all these different attributes. And so if you are going to go that route, I would highly suggest you take a look at this presentation from Michael Henrich from a year or two ago, where he introduces the message to IIO dictionary block. Great presentation, and a much more elegant way to implement these kinds of functions for any IIO device there. But what I want to talk about today is how to use Python with GNU Radio Companion to control Pluto or really any of our devices in this Python library. So why would you want to do this? Why not just stick with Python? If we're going to use Python, why not just stay in a Python IDE? Why combine it with GNU Radio Companion? Really, the reasons that I like it are really the GUI objects in GNU Radio Companion are fantastic. When you drop down a slider bar, it is so easy to add it into a Python program versus trying to build your own in tkinter or Qt in Python. It becomes just very cumbersome. Your whole program just explodes. And the way GNU Radio does, it's multi-threading. It's just a very smooth, seamless operation. The plots update quickly. It's a very slick, it's a very great user interface that is very, very easy to do. Why not to use it, or maybe some of the pain points, and this could be because of my own ignorance in GNU Radio. Maybe there are better ways to do this. But one of the pain points is the input-output buffer size, or at least the way that I implemented it. Shane implemented it a much smarter way using message passing, and that's the right way to do it. I didn't do it that way, but I do want to thank Wiley for his help and his advice on sort of what is the easiest way that I could do this and put this together. But the buffer size, the output buffer size, you just have to be aware of it, and you kind of got to work around it. But I'm sure there's better ways to do it. And then the other thing is that the IDE for Python and GNU Radio, there really isn't one. So I do everything in a text editor, and maybe there's a better way to do that, but it's very difficult to debug a Python script in GNU Radio. So I do most of my editing in Spider or PyCharm, and then once my Python script looks pretty good, then I import it over into this GNU Radio Python block. So how do we control any device from Analog Devices in Python? We use this PyADI IIO library. You can download it here. It's great. In Python, it's just import ADI, and that has all of the ADI objects, whether it's an accelerometer or a software-defined radio or a synthesizer or a precision ADC. Whatever it is, you're going to find that object in this ADI library, and then you just create an object of whatever you care about from that library. So if you're doing Pluto, it's just ADI.Pluto. You can also give it a context like a USB or an IP address, and then you assign attributes to that object. So here we're assigning the transmit and receive LO frequencies, and they're both set to 2.2 gigahertz. And then you either send or receive data from that object. And so here we're just getting a buffer of data. So it's very easy to use. It's very human readable. There's no weird names or anything in here. And it's very consistent across all of our Analog Devices products. So once you do it once and you switch to a different product, even if it's a totally different product, it'll be very familiar to you. So then you can take that Python code and you can put it into one of these Python blocks in GNU Radio Companion. So you can see that block there. All the other blocks are just GUI blocks I was talking about, like they're slider blocks or they're graphing blocks. And so kind of all the work that is done in my flow graph is in that one Python block, and then everything else is just a GUI object. So it's super clean. You can take a look at this code in flow graph. It's on my GitHub page if you want to, but again, with the caveat that I am neither a Python expert or a GNU Radio expert, so I'm sure there's better ways to do this, and if there are, I would love your help or contributions to kind of do these kinds of things. Here's what that flow graph looks like. If you just click run on that flow graph, that's on my GitHub site. So I'm sending out 4 FMCW chirps in the Python program, but you can see just how easy it is to use it's very fluid to use the slider bars, and it updates very quickly and stuff. I mean, it's not like a super impressive demo, but like to do this in Python is much more clunky. And it definitely clutters up your Python code, whereas I don't have to put any Python code in around outside of the actual work that I'm focusing on and that I'm doing. And so here's a time domain plot. You can see those 4 chirps going on there. And to learn more about how to incorporate that kind of Python code into these Python blocks, I highly recommend Wiley's presentation from a couple years ago. I have gone back to it several times. Great presentation, great information, and You can take a look at that. I've also created a wiki page for how to install the Pi80i programming Python library into your GNU radio installation. So I've tried it out and done examples for Windows using Radio Conda, Ubuntu 24 Linux, and then our Kuiper Linux on the Raspberry Pi. So if you go to this site, you can see step-by-step instructions on how to install GNU Radio, but more importantly, how to then incorporate the Pi80i IIO Python library into your GNU Radio implementation so that you can call it from this Python block. And then just a quick slide. If you do that, here's how you can check your installation, and you can make sure that you really have installed it and all the paths are correct and everything like that. Okay, so that was how to put Python into, or how to use our ADI Python library with GNU Radio Companion. Hope that was helpful. Now I want to talk about the new TDD engine. So when I ran that last flow graph, we did 4 FFCW chirps, and it looked like this, and they were all just kind of dancing around the screen. And if you've used Pluto before, you're used to seeing things like this. But check this out. Same program, one change though that we made, but now look, everything from the transmit buffer on the top row is synchronized with the receive buffer on the bottom row. So everything is time aligned and stable, and this is what allows us to do that kind of radar implementation. Okay, so how do we do this? We use this new TDD engine that's in Pluto. There is a TDD engine in Rev 0.38 of Pluto, but we're actually tweaking it and improving it a little bit. There was some timing things that we wanted to improve on, as well as some syntax that we wanted to change. So if you want to try this out yourself, download it from this link that's on there for now. And I think very soon, maybe in a month or so, there'll be a new version of the Pluto firmware that will have all of this incorporated into it. But essentially, how do we set this up? We create a TDD object. We assign attributes to that TDD object to control the timing. We trigger the start of the TDD engine, and that's going to then align our transmit and receive buffers. And then we read back those receive buffers and just do whatever we want with that data. I want to thank, in particular, Unit for all of his work on this TDD engine and stuff. I really appreciate it, and he's done a great job with it. It was a lot of work to figure all this out and put this all together. This TDD engine, this is what it looks like in Python. There's a bunch of attributes that essentially control the timing. The default values that I show here are pretty good values that if all you want is just to align the transmit and receive buffers, these values are going to work out well. A couple of caveats in there. You must be in cyclic buffer mode for transmit. This means you load the transmit waveform once and then it just repeats over and over. So you must be in that mode. When you're making changes to the TDD engine must be disabled, and then you re-enable it after those changes are done. A couple of notes in there if you want to read through them. And this is what that modified code now looks like. So it's the exact same code that we had run before, but now with that TDD engine included in that Python block. And this is what the whole timing profile looks like. If you really want to get into it, there's all kinds of, I suppose, kind of cool things that you could do with timing, including outputting pulses from Pluto, outputting GPIO pulses at a specific time or at a certain rate or a certain number of pulses, and I'll show you how we use that in a couple of slides. So there's actually quite a few things that you can do that are fairly powerful, more than just aligning transmit and receive buffers. You can trigger this TDD engine either from a software command or from an external GPIO. So here's a case where here's how you would do that triggering with external signals. You can trigger it on pin L12N of the little Pluto 14-pin GPIO header there. And if you have configured it to output pulses, which you do with these commands here, if you've configured that, those pulses will output on the next pin adjacent to that pin. So why would you want to do this? Why would you want to output pulses? I suppose there could be any number of reasons, but the reason that I want to do it is because I can then feed that pulse train into the ADF 4159 has a trigger input called TX data, and when TX data receives a trigger input, it will execute something. It will execute some frequency ramp or FSK step or something like that. So for radar systems, I can set that up so that it executes some 500 megahertz FMCW chirp every time that it receives a TX data input. So this is very cool, and it makes doing multi-chirp, the range Doppler plots that Shane showed, it makes those very easy to do. And here's if you put that all together with that external system and stuff, this is what it looks like, that range Doppler plot. Here's cars going past. And so this is 500 megahertz of chirp bandwidth, which we get, like Shane talked about, from that stretch LO processing. So this is what it looks like. This is with the TDD engine. And, okay, so let me move on now. I only have a few minutes left for the Pluto ESD diode issue. We, in an effort to fix something that wasn't broken, we added these ESD diodes to all the 4 of the RF ports on the Pluto Rev C. And it was a very noble effort. We thought, why not? Let's just add ESD diodes. And what we found out was that our manufacturer had a hard time with those diodes, and they tended to put too much solder paste underneath those diodes. And it was difficult for us to test this out because we do a lot of over-the-air testing. So the issue is that there could be solder paste underneath these diodes that essentially short an input or an output of these 4 RF ports out. And what that's going to look like is if you do a loopback test, if you loop back transmit to receive, you're going to see a much smaller signal. So in this slide, I've put just some parameters that you can try out on your Pluto, and to give you an idea of what kind of amplitudes you should expect to see. And if it's very low, you can remove the diode. If it's around these numbers, you don't have to remove the diode. I don't know. I remove the diodes on all of my Plutos. They're really not necessary. It would be extremely difficult to ESD zap the center conductor of one of these SMAs. So I remove all the diodes anyway. But if you don't see a problem, I guess you could leave them in. To remove the diodes, it's very simple because they're so tiny. The easiest way I found to do it is I just scratch it off with my fingernail. It scratches off pretty easily. And then what's left over is a little bit of solder and a little bit of pads from the ESD diode. And so just take some solder wick and you can suck up that extra solder. So there's on the lower right-hand corner, there's a picture of what that solder looks like beneath an ESD diode. So sorry about that. Hopefully your Pluto's okay, but if this is a way to check for it and hopefully fix it. And it could be on any of those 4 ports. The 2 transmitters, 2 receivers. In the last minute that I have left, let me quickly go over context port forwarding. This is a very cool feature. Say you had 4 Plutos a long way away and you wanted to connect them to your computer. How would you do that? There's actually a couple ways to do it, but you wouldn't necessarily have to run these super long USB cables. But a cool way to do it would be, why don't I connect these Plutos into a local Raspberry Pi, and then via Ethernet connection, I'll talk to the Raspberry Pi and it will control and stream data from all these Plutos. That would be very cool. And how would we do that? We do that by this new feature from libIO version 0.24 and above, where we have this context port forwarding. What is a context? A context is just a group of these IIO devices. So things connected to your Raspberry Pi through SPI or I2C form a context for the IIO devices. Pluto has its own context through USB. It's just this group of IIO devices. Before that, you might have to plug in maybe a Raspberry Pi to your laptop, and you might have to plug in Pluto to your laptop. Each one has a separate context, and then within Python or GNU Radio, you would address them and create objects. But now with context port forwarding, you can run an IOD service right on the Raspberry Pi that you can assign a port number to whatever IIO device like Pluto and do that. This is what it looks like. If you just run this command on your Raspberry Pi, you can assign a unique port number to the Pluto device that you have connected to that Raspberry Pi, and that will forward right out into your computer via Ethernet. And you can see that if you open up IIO Oscilloscope and hit refresh and scan for all IIO contexts, it will find that over that Ethernet cable, and it will report back to you. It is, in this case, it's called phaser.local :50,901. But you could do that but you can do that automatically. I'll share these slides. These are some scripts that Mark Thorne has put together to do that automatically at startup. It will start up the service. And of course, you could do that with multiple Plutos together. Here's 4 Plutos, each has a different IP address, and each has a different port that we're forwarding it to, and all of these can be interacted from a long distance away from your computer running MATLAB or GNU Radio or Python or whatever. It doesn't have to just be Plutos and devices like that. You can also do this with serial backend devices, really any IAO device, whatever context it has or way, you can forward it using this service here. Okay, so that's it. Just a quick update on Pluto, some new things that we're doing, and hope that was helpful. Thank you.